Welcome to the Explainer. Today we are diving into a really common trap people fall into with data. We're going to look at a powerful statistical tool that unmasks the true shape of your data and shows you what a simple average might be hiding in plain sight. So here's our game plan. We'll kick things off with a neat little statistical puzzle. Then, to solve it, we're going to introduce the concept of moments and really zero in on the third one, that's skewness. After that, we'll get practical and learn how to interpret it, and finally, we'll see why this one idea is so incredibly important. Okay, let's get right into it. To set the stage for our puzzle, I've got one simple but really important question for you. Look, whenever we get a new data set, what are the first two things we look at? The mean, the average, and the variance, or how spread out everything is. But what if I told you that these two trusty numbers don't just tell an incomplete story, sometimes they can actually hide the most interesting part of it? Okay, check this out. Imagine two completely different sets of data. The one on the left is perfectly balanced, right? Symmetric. The one on the right, though, is clearly lopsided. Now here's the real head scratcher. It's totally possible for both of these data sets to have the exact same average and the exact same spread. Their centers are identical, their variance is identical, but you can see with your own eyes they are not the same at all. So how in the world do we capture that lopsidedness with a number? Well, the solution to our puzzle and the key to describing a distribution's shape lies in this really elegant concept called statistical moments. In statistics, moments are just a set of measures that, together, describe the shape of your data. And the fingerprint analogy here is perfect. If the mean and variance are just the first two prints you check, the moments give you the full, detailed set, creating a totally unique profile for your data. And this breaks it down so nicely. The first moment is the mean. It just tells you where the center is. The second moment is the variance. It tells you how spread out the data is around that center. But the third moment, that's our hero today. It's called skewness, and its whole job is to measure the asymmetry, that lopsidedness that was causing our puzzle. So let's really zoom in on this third statistical moment, which, as you now know, goes by the much cooler name skewness. So what is skewness? In the simplest terms, it just tells us if our data is nice and balanced, or if it has a long tail stretching out to one side. It is literally a measure of lopsidedness. If your data is perfectly symmetric, its skewness is 0. Okay, so how does the math work? Well, remember variance, the second moment? It squares the distance of each data point from the mean. Skewness, on the other hand, cubes it. Now, why cube? Think about it for a second. When you square a negative number, it becomes positive, right? So you lose all information about whether that data point was above or below the average. But when you cube a negative number, it stays negative. This one little mathematical trick is the key. It preserves the direction of the outliers. So when you average all those cubed differences, you get one number that tells you not just if your data is lopsided, but which way it's leaning. All right, so we have a number. We've calculated the skew, but what does a positive number mean? What does a negative one mean? Let's figure out how to actually read this thing. This table really lays it all out, but here's the absolute key relationship to get. Skewness pulls the mean away from the median. If you have a positive skew, that long tail of high-value outliers on the right pulls the average up. So the mean is greater than the median. And with a negative skew, it's the opposite. The low-value outliers drag the mean down, so it's lower than the median. Okay, let's start with our first case, a positive or right-skewed distribution. The absolute classic example of this is income. Think about it. Most households are clustered around a certain income level, but then you have a few billionaires, right? Their massive incomes create this super long tail stretching out to the right. And those few outliers pull the average income way, way up. This is exactly why you always hear economists talk about the median household income. It gives you a much better picture of a typical family situation than the mean does. Now for the ideal case, our baseline, where there's no skew at all, the symmetric distribution. This is the dream scenario. Everything is perfectly in line. The mean, the median, and the mode, which is the most common value, are all exactly the same. The classic bell curve is the poster child for this, and it's the bedrock assumption for tons and tons of statistical models. And finally, let's look at the mirror image of our income example, a negative or left-skewed distribution. For this one, picture an exam that was just way too easy. Almost everyone in the class gets an A, so the scores are all bunched up on the right side, between 90 and 100. But maybe a couple of students didn't study at all and got really low scores. Those few scores create a long tail to the left, and they literally drag the class average down. So the mean score would actually be lower than the median score, which would better show how the typical student actually did. Okay, this is all interesting, but so what? Why is this idea of skewness so fundamentally important for anyone who's looking at data? Here's the bottom line. You should think of skewness as a giant red flag your data is waving at you. First, it screams, hey, look over here. There are outliers, and they might be distorting everything. Second, it tells you to be really suspicious of the mean as your measure of what's typical. And third, it's a huge warning that many of the standard statistical models you might want to use, which assume your data is symmetric, could give you totally wrong answers. And really, this quote says it all. This is the practical take-home advice. The second you see significant skew in your data, your first thought should be, maybe I should use the median instead of the mean. The median isn't affected by those extreme outliers, so it often gives a much more honest picture of your data. So, we've solved our puzzle. The third moment, skewness, gives us this amazing lens to see the lopsidedness in our data, but you know how it is. Answering one question just leads to another one. What about how peaked or flat a distribution is, or the thickness of its tails? Well, that's a job for the fourth moment, something called kurtosis. And that's a story we'll tackle in a future explainer.